This lesson is going to concentrate on the concept of complements and how we use them in probability. Suppose we let the event R be that it will rain. And suppose we go to a weather person and they give us their expert opinion and they say, well, the probability of event R that it will rain is going to be equal to 0.4. Now, what does that mean? So in the world of weather, they don't say there's a 0.4 probability. Instead, they say there's a 40% chance. So remember, percentages are just probabilities times 100. Complements in probability represent the possibility of something not happening. And we symbolize it by just putting a exponent looking or a superscript capital C. So what would we do here? If we were to symbolize that it will not rain, we would do this. And this would be the event. So R with a capital C in the superscriptor looks like exponent, it's not an exponent, would be it will not rain. So the question is how would we find the probability of RC? Well, if you ask most students, well, what the probability of it not raining would be if it's 40% that it will, their brains are going to go to, well, 100% is the total. So 100% minus 40% is going to give us 60% chance of not rain. Well, in the world of probability, it's a little bit different. 100% for percentages is the equivalent to 1 for probability. Therefore, you would do 1 minus 0.4, or in other words, 1 minus the probability of R, which is 1 minus 0.4, and we would get 0.6, which equivalent is 60%. So 0.4 probability that it will rain, 0.6 that it will not. So to be super technical, basically if we have some event E, then the probability of E's complement is always going to be equal to 1 minus the probability of E. This is the complement rule. So most students have the complement rule already baked inside of their heads because of the whole concept of 100% minus. Something for percentages, that's something they've done in their life a lot or thought about in math classes, etc. So you just have to sort of tweak it now. When you're doing probabilities, it's going to be 1 minus. Okay, just a small footnote when it comes to this formula. Hypothetically, we can actually write it in two different ways because technically we can say that the probability of an event is also equal to 1 minus the probability of its complement. This should make sense because if we had switched this 0.4 and 0.6, then 0.4 is also equal to 1 minus 0.6. So just the reason why I put this up here is sometimes there's problems where it can look a little confusing when you're putting the event in and its complement, but just realize that either one of these is legal in terms of using complements. So when it comes to using the complement rule, we don't do a whole lot of high-level probability computations really with it because it's pretty simple. But I often call it the formula of convenience, the main probability formula that will maybe make some computations a little bit more simple than it could be. So let's look at an example of where that could happen. Okay, so the following is a frequency distribution of household income collected by the U.S. Census in 2013. A total of 122,953,000 households were described below. So just a note here, in basically the table that we have here, the frequency distribution, it's going to list the income spans, and then it's going to have a number here. This number has 3 more zeros on the end of it. So this number actually represents 8,940,000, but so that our numbers and our calculations are easier to deal with, we just remove the 3 zeros It makes life easier for us. Okay, so let's look at what this problem is asking. It says, compute the probability that a randomly selected household earned the following incomes in 2013, specifically less than 200,000. It looks like they're trying to guide us to use the complement rule, but we probably want to discuss why. So if we look at the quantity less than 200,000, you can clearly see that the value 200,000 is actually listed here in the category 200,000 or more. So it would make sense that this problem is actually asking for anything less than that. So what does that exactly include? Well, that's going to include all of these values right here. So one of the things that you want to get used to when doing problems like this is to take the easier avenue when it comes to computations in probability problems. For example, right now so note that I do have the sum of all the numbers right here, so that's helpful. I could right now add up all of the blue highlighted numbers, right? Because that's less than 200,000, all of them are. And then I could divide by 122,953, and I got my probability. Many students might even choose to take that route in order to find this, but I think it's just too much work. Because the reality is the complement rule can actually get us there faster. How? Well, let's just say we define this as the event E. Then, using our second rule here, the probability of E should be equal to 1 minus the probability of the event E's complement. Okay? So if you look at all of the blue highlighted, which I bracketed in red over here, there's only one item that falls in the complement of this scenario, and it's 5,913. Which means I should be able to do 1 minus the probability of this occurring. So we know there's 122,953. Well, how many are there? There's 5,913 out of that. So all I would have to do is the probability of this event and then subtract that from 1, and I'm already done. I don't have to add up all these numbers to get that done. So what does that look like? Well, if I do the calculations for this, I'm going to get approximately 0.9519 as my probability. If you get into the habit of using this rule, rather than doing a whole lot of extra work, it can really be beneficial for you. Okay, just a quick note here. So everything I've done so far with this particular lesson is from section 5.2. And everything that I'm about to do is from 5.3. So this is the video lesson itself is a little bit of a mix of various topics that happen to go together. So I just put them together in this video. Okay, we're now going to focus our attention on a specific genre of problem from section 5.3 called an at least one problem. An at least one problem's goal is to basically utilize both the multiplication rule and the complement rule in one problem. Let's use an example to introduce the concept. It says, in a giant tub of toys, it is estimated that 19% of those toys are new. If 9 children randomly select a toy, what is the probability that at least one child selects a new toy? Okay, so we're basically given two pieces of information here. We're given that we have 19% of the toys are new in the giant tub, and that we have 9 children that are going to be picking toys out of that giant tub. Our focus is to find the probability that at least one child selects a new toy. We'll call this the event E. Before we get into any formula or probabilities, I think it's really valuable to take a look at this in terms of more of a conceptual thing. So let's say you had 9 children. and they're each going into the tub, giant tub, to select a toy, then what are the options for how many could actually get a new toy? Well, those options are as follows. We could have nobody could get a new toy, one of them could, two of them could, and we can keep on going all the way up until how many children there are, which is 9. Which means all of the numbers that I just wrote here are all the possible scenarios for number of children that get a new toy. Now note, we're looking for the probability that at least one child gets a new toy. So remember, at least one means one or more. So we're basically looking at this and we're going, okay, so you're asking us to find the probability of all of these, which means I would have to go in and find the probability that one child gets a new toy, then that 2, then that 3, and so forth. That actually is a lot of work, because in order to do this problem, I'm going to have to use the multiplication rule and various other methods. Okay, so what's the alternative here? What could we do to make our lives easier? Well, if this is the event E, which means all of these, then what's the complement of the event E? It is 0, as in none of the children end up getting a new toy. And it turns out that in general, at least one problems focus on this one important concept that I just mentioned. So often we say, whenever you want to find the probability of at least one of something, then that's always going to be equal to 1 minus the probability of none of it. So why is that? Because this is our event and this is our complement, just like we noted over here, right? So this fits perfectly with the whole idea of the complement rule. So for this and any other at least one problem, our focus now is simply on finding the probability of none. So in other words, finding the probability that no children select a new toy, because if we can find that, all we'll have to do is subtract from 1, and we have our answer to our actual problem that we're looking for. So let's start with this. The one piece of information that's given in this problem in terms of probability is the probability that one randomly selected child, whoever that is, selects a new toy. And that probability is 0.19, given to us as 19% in our problem. So next, if the probability of one child selecting a new toy is 0.19, then the probability of one child not selecting a new toy is its complement, which is going to be 1 minus 0.19, or 0.81. So in 19, it's just like the example above when we were talking about it raining. So if it's 0.4 that it will rain, it's 0.6 that it's not. Same thing here. If it's 0.19 that they select a new toy, it's 0.81 that they don't. Okay, so this is when it gets a little trickier. Our problem is not asking for just one child picking a toy, like these probabilities over here are insinuating. Instead, it's asking for 9 children. Okay, so in order to accomplish a probability for 9 children, we're going to need the multiplication rule. So just as a random example of this, using our first probability here, if I want to know the probability that all 9 children end up with a toy, then what would that be? That would be like saying, what's the probability that child number 1 gets a new toy, and then child number 2 gets a new toy, and then child number 3 gets a new toy, and so on and so on and so on, until you get to the 9 children. Well, how would you find that? It actually wouldn't be too tough. You'd basically just take 0.19, and you would take that to the 9th power, just like you've seen earlier in the multiplication rule section video. But this problem is not asking for all 9 children. It's asking for at least one child selects a new toy. Well, we've already determined that the probability of, write it over here, the probability that at least one child gets a new toy is the equivalent to, according to this here, that 1 minus the probability that none get a new toy. Okay, so if that's the case, then we need to find this. Now, some students right away will look at this and be like, well, isn't that this number? No, that's the probability for any one child walking up and grabbing it. What do we want? We want it for all 9 children. So what if all 9 children went up there and none of them ended up getting a toy? Then that would be the probability of one child not getting a toy, and then the next child not getting a toy, and then the next. So if you're following me from what we did here when we said, oh, 0.9 to the 9th is going to give us basically this probability here for all 9 children getting a toy, then the same logic should fall for this one, that 0.81 to the 9th should give us none of the children getting a toy. Therefore, believe it or not, this is what's going to give us the probability that we're looking for. So just be careful with the calculations. Make sure you do this first and then subtract from 1. Every once in a while, students mess up parentheses or things like that. Be careful with that. If you do this, you're going to end up with approximately 0.8499 as your probability. Okay, so let's just do one more problem here just to make sure that this is all good, because this often is a bit of a mind bender for students. So it says a multiple choice test consists of 6 questions with 5 choices each. What is the probability that a student guessing at every question gets at least one question correct? Okay, so the probability is that we will get at least one question correct. So basically that's our event that we're looking for. So immediately we can go, okay, probability at least one question correct is what we're looking for. Now, without going through that entire explanation we did in the last problem, this should be more straightforward. Why? Because we know from our formula up here, right, this formula here, that the probability of at least one of something is always going to be equal to 1 minus the probability of none. So it's going to be none are correct. Okay, so let's do some of the side work that we did before, but also for this problem. So remember, we are dealing with 6 questions here, but the initial given information with the fact that there are 5 choices is only going to deal with one question. So we want to start with what that is. So if there are 5 choices, then you have a 1/5 likelihood that you're going to guess correct, which is 0.2 basically. But that's only on one question. So let's get that written down. So the probability of guessing correct on one question is going to be exactly what we said it was going to be, 1 out of 5 or 0.2. But remember here, this implies that we don't want, none of them are going to be correct. So we don't want guessing correct, we want not guessing correct. So therefore, we're looking for the probability of not guessing correct on one question. Okay, this of course is going to be our complement rule. Our complement rule is going to tell us that 1 minus 0.2 is 0.8. Which means that there's an 80% chance you're going to get any one question wrong. But our problem is not asking for one question wrong, it's asking for 6 questions wrong. So what's the probability you get the first one wrong, and then the second one wrong, and then the third, all the way up to the 6 questions? Well, that is going to be 0.8 to the 6th power. So we're doing 1 minus this probability, which is 0.8 to the 6th. If we do that calculation, we're going to get approximately 0.7379 as our result.